Okay, so we should be recording. So these problems 7 through 10 are in reference to a new piecewise function. Again, it's just three line segments that have been pieced together. Let's take a look and see if we can't apply our function transformations to this graph of f. They're calling, yeah, there it is right there. They're calling this graph f. So in problem 7, we have a new function g that's related to this graph of f, and this time we have two transformations. We have a transformation on x, and outside the parentheses we're adding to the output of this function, we have a transformation on y. Now, we've seen before that inside the parentheses, when your transformations are on the domain on the x values, it's bizarre in its behavior. So I'm expecting that -1 is actually going to result in the graph shifting the graph to the right 1 unit, and this +2, it's normal in its behavior that positive is up and negative is down, and I'm expecting to see that this is up 2. So if I try to fill in this table, how could I do that? Well, let's see if we can determine what g is evaluated at -1. On the right hand side, everywhere I see an x, I replace it with -1. So instead of x minus 1, it's -1 minus 1, and then it's +2. So this is f evaluated at -2 plus 2. Well, from my original table, f evaluated at -2 is 4. And 4 plus 2 is 6. So what I have is -1, 6 is a point that's on the graph of g. Suppose I try to evaluate this function g at 1. Well, everywhere I see an x, I replace it with the number 1. So I have f evaluated at 1 minus 1 plus 2. 1 minus 1 is 0. And my table tells me that f evaluated at 0 is 3. And 3 plus 2 is 5. So what this is telling me is that when x is 1, the output of this function g, the y-coordinate, is 5. Now, let's come in and evaluate g at 2. F evaluated at x minus 1 is f evaluated at 2 minus 1 because x is now 2, and then plus 2. 2 minus 1 is 1. From my original table, f evaluated at 1 is 0, and 0 plus 2 is 2. So g evaluated at 2 is 2. What about this other one? What if we try to evaluate g at 4? That is f evaluated at 4 minus 1 plus 2. 4 minus 1 is 3. And my table tells me that f evaluated at 3 is -1. And -1 plus 2 is 1. So I've got 4, 1 is a point that's on the graph of g. So let's come in and plot these points and see if we're right that we observe that we're going to take this graph and shift it to the right 1 unit and then shift it up 2. So let's plot the point -1, 6. -1, 6 is up here. 1, 5 is here. 2, 2 is approximately right there. And 4, 1 right there. So what do we get? All right. So let's take a look at this point. If we move to the right 1 unit, we'll be here. And then if we go up 2 units, we'll be there. So we saw that the point 3, -1 is transformed to the point 4 comma 1. And it's transformed through these two transformations. Go to the right 1 and up 2. What about this 1, 0? What point is it transformed into? Well, if you go to the right 1 unit and then you go up 2 unit. Well, I didn't go. I should have, when I eyeballed it, I kind of scooted over to the left there. That point should be maybe a little bit to the right there. The point 2 comma 2, I just did a poor job in plotting that point. But if you go to the right 1 and up 2, you're at that point. What about this 0, 3? If we go to the right 1 and up 2, you'll be at 1, 5. So this 0, 3 is transformed into 1, 5 through these two transformations. So you want to begin to looking at it. How did I fill out that table? How did I know to come in and say that G evaluated at -1 when over here I didn't even have a -1? Because I knew that moving to the right 1 was to add 1, so I knew that -2 plus 1 was a -1, so I added that so that it would work out that I got 6 here. Let's take a look at this. Now, this time we have what we refer to as a non-rigid transformation. I'm going to think of these guys as stretching or shrinking. Instead of thinking of toothpicks that move to the left or to the right, up or down, or reflect across one of the axes, here I'm going to either have a vertical stretch or a vertical shrink from an axis. So these line segments are going to stretch and shrink. They're not going to be rigid. That's why it's referred to as a non-rigid transformation. And being inside the parenthesis, affecting the domain, affecting the x, it kind of the result is kind of an unexpected behavior. It's kind of bizarre. Let's see if we can fill in this table. So suppose I'm interested in evaluating G at -1. Can I figure out what the output would be when x is -1? Well, this equation is telling me that I can use the table of f if I take 2 times -1, which positive 2 times -1 is a -2, and f evaluated at -2 is 4. So I know that -1 comma 4 is going to be a point that's on the graph of G. Here, if I evaluate this function G at 0, then f of 2 times 0 is f evaluated at 0, which we know to be 3. So that point, 0, 3, that's a point on the graph of f, is also going to be a point on the graph of G. It wasn't transformed at all. All right, let's come over. Let's evaluate G at 1/2. Well, my equation says take 2 times x. Well, this time x is 1/2. 2 times 1/2 is 1. And f evaluated at 1 is 0. So when x is 1/2, the output y is 0. We won't have to do this every time. We're only doing this the first time just to observe the relationships and these patterns so that in the future we can just jump in and we know the patterns. We know the observations. G evaluated at 3 is f evaluated at 2 times 3. You know what? I won't be able to figure that out because f evaluated at 6 is not in my table. I need to be a little bit smarter about what I'm evaluating here. So what about G evaluated at 3/2? That's f evaluated at 2 times 3/2. And 2 times 3/2 is just 3. And f evaluated at 3 is -1. So when this is 3/2 the y-coordinate is -1. So let's plot these points and see what we observe. -1, 4 is here. 0, 3 we've already plotted. 1/2, 0 is, say, right there. Just going to have to eyeball it. 3/2 is about 1.5, and then if I go down 1 is there. So if we connect the dots, what do we have? Connect the points. So we were affecting the x-coordinate, and you might expect that if you double the x-coordinate that it would stretch. But what really happened is this was a horizontal shrink. These points moved in closer to the y-axis, and they did it by a factor of 1/2. We take the reciprocal of 2, which is 1/2. So to obtain the graph of G, we horizontally shrink the graph of F by a factor of the reciprocal, and the reciprocal of 2 is 1/2. Let's take a look at this problem number 9. This time the multiplication is not affecting the domain, is not affecting the x-coordinate, it's affecting the output of the function, the y-coordinate. So all of these x values are going to be the same, and we're going to take 2 times the y values. If you don't see that, let's plug in some points. If we evaluate G at -2, what will we have? We'll have 2 times f evaluated at -2, and f evaluated at -2 is 4, and 2 times 4 is 8, so -2, 8 is going to be a point on the graph of G. If I try to determine when x is 0, what's the y-coordinate on the graph of G, I can do it through this equation, that 2 times f evaluated at 0. F evaluated at 0 is 3 from my table, and 2 times 3 is 6. So 0, 6 is a point on the graph of G. When G is evaluated at 1, that's 2 times f evaluated at 1. F evaluated at 1 from the table is 0, and 2 times 0 is 0. So I know that the point 1, 0 is a point that's on the graph of G. If I try and determine what G is evaluated when x is 3, that's going to be 2 times f evaluated at 3, and from the table, f evaluated at 3 is -1, and 2 times -1 is a -2, so that means the point 3, -2 is going to be on the graph of G. So let's plot this and see what happens. We notice that all of these x-coordinates stayed the same, and these y-coordinates, they've been multiplied. It's these y-coordinates multiplied by 2. So we are vertically stretching the graph by a factor of 2. -2, 8 is off the graph, so I'm going to have to estimate it. If that's 6, 7, and that's 8, so that's up here. Sorry about that. 0, 6 is right here. 1, 0 is there. Because, when you multiply the y-coordinate by 2, 0 times 2 is still 0. So we're stretching it, vertical stretch, we're stretching it away from the x-axis. and 3, negative 2 is here. So let's connect the points. So what do we observe? We observe that this y-coordinate of 4, that this got stretched by a factor of 2, and that the coordinates of that point was negative 2, 8. The point here at 0, 3 got vertically stretched. That y-coordinate of 3 became a 6. So 0, 3 got vertically stretched away from the x-axis to the point 0, 6. Since this point was on the x-axis, you can't stretch it away from the x-axis. That point is a point on our graph of G. Now, this was 1 unit below the x-axis, so when you stretch it away from the x-axis by a factor of 2, this point stretched down to negative 2. So this is 3, negative 2. So hopefully that helps. Oh, we've got one more. Now this one we're going to have to spend some time on. I'll do it in a separate video. I want to cut and paste the order transformations because that we've got one transformation, the +1, we've got another transformation 2, we have a third transformation of 1/2, a fourth transformation with the negative sign, and a fifth transformation with shifting it down 1 unit. So this is going to deserve its own video, separate video, and we may have to come back to this as we get more experience. So for number 10, it may very likely be that I'm just showing you the answer and stuff, and you're going to have to refer to it to help you gain experience. I'm just trying to point out that this is a difficult problem when you have a lot of transformations going on.